Today, we're going to look at angle of elevation and depression. And basically, these are just descriptions we can give of the angles we're going to have in real life scenarios. Specifically, both of these angles are always made between the line of sight of someone and they're looking up or they're looking down at an object. And we can use that angle as well as other measurements to find out other heights, kind of like we did indirect measurement with using shadows and such when we did similar triangles. So in our first diagram, you notice we have angle of elevation. So we have our person sitting down at the bottom looking up. So their line of sight goes directly to the top. In this case, it's a lighthouse. The angle of elevation is how much they would actually have to tilt their head up in terms of comparing to if they were looking straight ahead versus tilting up to the top of the object or the lighthouse. Angle of depression would be how far they have to tilt down. So if we think about our person in the lifeguard chair in our second picture, their line of sight going straight out, well, that wouldn't help out too much. They are going to look down to see people at the pool and make sure everybody is safe. However, as I'm highlighting things, there's another thing that I could highlight. And so we have this kind of baseline down at the bottom of our triangle that we see, kind of our water level. And do you notice anything about the person's line of sight up at the top with the water level? Well, wait a second. Those are actually parallel lines. And so if we think back to parallel lines, when we were looking for congruent angles, we use this a lot in our similar triangles and our congruent triangles. We have our angle of depression and actually the angle of elevation. If we change our perspective, think about the person looking up from the water at the lifeguard. Well, those are actually alternate interior angles. And so technically in any of these problems, the angle of depression and the angle of elevation are always going to be congruent. So we need to think of that in terms of what pieces we label what our perspective is. But those are always going to be congruent angles. And additionally, in our third diagram, sometimes we're going to have to take into account that person's actual height. So if we're actually measuring objects that aren't quite as tall, where somebody's height at, 5 feet, 6 feet, whatever, that's going to be significant compared to the height of the object we're trying to figure out. And so we'll look at a couple of problems with that as well. So let's go ahead and jump in. Our first example, we're going to look at the angle of elevation of the sun when a 12.5 meter tall telephone pole casts an 18 meter long shadow. So in this case, we're going to imagine if we had somebody sitting down at the base point, person, bug, cat, whomever. And so the angle of elevation of the sun is if they were to look to the top of the telephone pole and line their sight up with the sun, which of course we would never want them to look directly at the sun, that makes our angle of elevation. And so I'm going to go ahead and mark that as theta. I don't know what that measurement is, but this now looks kind of like one of those problems where we were solving for our angles last class, and we just need to set up our ratios. So compared to our sine, compared to our angle of elevation, 12.5 is our opposite side, and 18 meters is our adjacent side. And so then that means opposite and adjacent, I'm looking for which ratio? That's our tangent ratio. So I could write my equation, tangent of theta, tangent of our angle of elevation, equals 12.5 over 18. And when we're solving for angles, that's when we used our inverse function. So I can rewrite my equation. Theta is going to equal tan inverse, or tan negative 1, of 12.5 over 18. And we type that directly into our calculator. Again, if you're using the calculator on your phone, you do want to make sure that you are in degree mode. And I would absolutely, if you are using your phone calculator, please use the Desmos app. There are other pieces involved if you're using your scientific calculator on your phone. If that is your only option, please do ask for help. All right, tan inverse of 12.5 over 18. I plug that in and I'm going to get approximately 34.7778 degrees. So that is my angle elevation how much somebody would have to tilt their head up to see the top of the telephone pole if they were standing at the edge of the shadow. Alrighty, example 2. This is one of our added height problems. If someone whose eyes are 5 feet above the ground is standing 100 feet away from a water tower and has to angle their head up by 52 degrees to see the top, how tall is the water tower? So as we're looking at this, we actually see 2 shapes in our diagram. So we've got the triangle that's made with the line of sight and the distance away from the water tower. But the height of our triangle, you'll notice, doesn't take up the entire height of the water tower. But we are going to start with this triangle because I know angle of elevation, 52 degrees. We know the base is still that 100 feet. And we can find the height of that triangle. So let's start there. Again, 52 degrees is opposite, or x is the opposite side, 10 is the adjacent side. So that means, yet again, we need to use our tangent ratio. So that's what I'm going to start with. Tangent of 52 degrees, our angle of elevation, equals our x over 100 feet. So I multiply both sides by 100, gives me 100 times tan, 52 degrees equals my x, and I just plug that in. So x is approximately equal to 127.9942 feet. However, again, this is an added height problem. So that means we need to adjust for the height of the person and their extra perspective from where they were measuring out their height. So the height of that 5-foot person, where their eye level starts looking up, we need to actually add that on to the bottom of our triangle. So that means the height of our tower is actually going to be whatever x plus that extra 5 feet is. So that means tower height is going to be x plus 5. In other words, it's going to be our approximate answer, about 127.9942 plus the 5 feet from the perspective of the person. And that adds up to be approximately 132.9942 feet. Now you'll notice I'm leaving my answers rounded to the nearest 10,000th. Again, I'm trying to stay very accurate, but keep an eye out for your problems. Sometimes they'll have you round to the nearest 10th, 100th, maybe even to the nearest foot. But as long as I'm pulling those 4 decimal places along while I do my work, my answers will still be pretty accurate. Alrighty, our next problem. Let's take a look at the helicopter. However, you'll notice we do not have a picture on this one. So we do need to go ahead and draw this out. We have a pilot in a helicopter, spots a landing pad below. So again, forgive me, here's my helicopter. And I'm going to imagine this is one of those glass bottom ones. So the person that's sitting in the cockpit can absolutely see straight out. They can see straight down. But if they're landing, the landing pad's probably going to be kind of offset a little bit. So here's my triangle that I'm going to draw. Alrighty, the angle of depression is 73 degrees. So they had to tilt their head down by 73 degrees. So again, that's always by line of sight compared to, if they were looking straight out. But again, that line of sight straight out from the helicopter is absolutely parallel to the ground. So our angle of depression that we labeled is actually the same as the angle of elevation if somebody was down at the ground looking up at the helicopter. I can keep labeling. So the horizontal distance of the pad is 1,200, or to the pad is 100 or 1,200 feet. All right, what is the altitude of the helicopter? However, altitude really means height. So we are solving for the height at which the helicopter is sitting. Alrighty, so again, I'm going to do everything in reference to the angle that's inside the triangle, which means my x is my opposite, my ground level is my adjacent. So that means we are going to be using tangent again. Now, are we always going to use tangent on all of our problems? No. However, it's a lot easier to measure a horizontal or a vertical distance than it is to measure that diagonal distance. So you'll find that a lot of word problems use tangent instead of sine or cosine. But again, the scenario may use the others. Always be careful, label your diagram, and then you'll be able to figure out which one to use. So again, to get x by itself, I have to multiply both sides by 1200. And now x will be completely by itself, so I just plug that right straight in my calculator. And so that will get approximately, the height is 3925.0231. So the helicopter is 3,925.0231 feet above ground level. Alrighty, our last example, and then there's a couple for you to try out. So multiple parts, real life scenario. Let's say somebody needs to climb over a 50-foot wall for whatever reason. Alrighty, so would a 51-foot ladder actually be long enough to get up to that top of the 50-foot wall? So let's double check. So let's see here. If the ladder is 51 feet, so let's go ahead and label where that would be on the triangle. The wall is 50 feet tall. What do you think? Well, technically, the ladder is taller than the wall, or longer than the height of the wall. So that means we would be able to angle it out from the base. So feasibly, yes, that should work. So yes, taller or longer than the height of the wall. However, anyone who has used a ladder knows that we have to be careful. So OSHA requirements, so that's the Occupational Safety and Health Administration. They actually have requirements as what you have to set your ladder to. So they state that a portable, non-self-supporting, so one of those extension ladders maybe that you've seen people use, has to be placed in an angle of 75.5 degrees from the horizontal. So in other words, our angle of elevation, where we at the bottom of the ladder looking up at the top of the wall, that angle has to be 75.5 degrees. So is that going to be enough with a 51-foot ladder? So let's actually solve for that angle that we have in this scenario and see what happens. So we know the height of the wall is 50 feet. So that's going to be our opposite side from our angle. 51 is our hypotenuse, our ladder. And so we can use sine. So sine of our angle theta is 50 over 51. So that means I actually have to use our technique from last class. So theta is sine inverse of the 50 over 51. And we just plug that in our calculator. And I have a problem. So when I plug that in, I got out 78.6351 degrees. So that means the angle is too large. So in other words, this is not safe. Not quite safe. So this would be one of those scenarios that if that's all you've got, you definitely have to have a spotter, somebody standing at the bottom of the ladder to make sure that it doesn't come out from underneath if somebody's on there. So then that begs the question, how long would the ladder need to actually meet those OSHA requirements? So let's change our diagram a little bit. We've got another diagram we can draw it out on. So we have to figure out what is the possible length of our ladder. The height of the wall is not going to change. And our angle, we're saying we are trying to set this angle to that 75.5 degrees. So we still use sine because 50 is still our opposite side. X is our hypotenuse compared to our angle that we're referencing. And so sine of 75.5 degrees equals 50 over x. And so again, we need to get x by itself. You can go through the official multiply both sides by x and then divide both sides by sine of 75.5, or we can use our shortcut. Oops, sorry. Since we've already done that problem over and over again, we know that this would work. So 50 over sine of 75.5 degrees. We plug that in the calculator and we get 51.6450 feet. So actually, it doesn't have to be that much longer, just about a foot and a half, a little more than a foot and a half longer to meet our standards. Alrighty, so that's the end of our required examples. However, if you'd like to see the U-Try problems, definitely take a look at part 2 of the video that I'm going to post.